Whenever we're working with solutions, it's important for us to know how much solvent and solute are present, and we get a handle on that with concentration. So concentration is important because when we're looking at solutions, the relative amounts of solvent and solute can change a lot of the properties, or can tweak a lot of the properties of the mixture that we're looking at. So we use concentration to describe relative amounts of solute and solvents. There are a lot of concentration units possible, right? If we're just talking about this relative amount of solvent and solute, pretty much any way we could measure the amount of solute or the amount of solvent or the amount of solution, we can mix and match those to get a lot of different concentration units. So let's pay very close attention to concentration units when we come across them, and we'll take a look at some of the more common ones that we'll come across. So the first big family of concentration units that I like to start with is fraction-based units, because fraction-based units are things that really kind of make sense. They really get to the heart of that relative amounts, because fraction-based units really are just a ratio. So the fraction-based unit is the amount of solute divided by the amount of solution. So the amount of solution is everything that's there. The amount of solute is just the amount of solute. How do we express those two? Well, how can we express amount of anything? We can use a lot of different units. We can use mass or volume or a bunch of other things that we've already used when we want to express amount. And we can, to some extent, mix and match those around a little bit to get a fraction-based unit. Now, fraction-based units make sense, but sometimes those fraction-based units are pretty small. So how do we address that? Well, let's just multiply it by some amount. If we multiply a fraction-based unit, or a fraction unit, by 100, we get a percent. You all know percents. You do them all the time, right? And this makes perfect sense, right? Percent, it's per 100. So take that fraction, multiply by 100, and you get the percent. If it's an even smaller amount of solute, we might want to multiply it by 1,000,000 to get a part per million, right? Part per million, percent, same idea, just a different multiplier, or even a part per billion if it's a really small number. So the whole reason these units exist, especially part per million and part per billion, is kind of gets back to some of the things we talked about with sig figs, right? Why do we use sig figs? Why do we look at things like scientific notation? Well, because having a lot of zeros around can be hard to keep track of, right? If I've got something that is a part per billion and I just express it as its regular fraction, there are going to be a whole bunch of zeros in front of my digits of information, and in transcribing those and communicating those, I might accidentally drop a zero or add a zero, which could lead to some big problems, depending what we're talking about the concentration of. So part per million, part per billion, percent, or just straight up fraction are all really the same unit. It's just a matter of scaling it so that you get a number that is a little bit easier to read and communicate. Probably the most useful and the most common unit that we're going to work with is a unit called molarity. And molarity is kind of a fraction-based unit, but what fraction are we working with now? We're looking at moles of solute per liter of solution. So I think you can probably see why this is such an important unit. We've got a lot of things that rely on moles. So having a way to express moles in a solution is pretty important. And that's where molarity comes in. So let's take a look at an example. What's the molarity of a solution made by dissolving 14.283 grams of glucose in enough water to make 150 milliliters of solution? So pretty straight up here, 14.283 grams divided by grams per mole. This is the number off the added up off the periodic table for glucose, C6H12O6. That gets us to moles. Divide by liters. I converted my milliliters up to liters, and I get up to 0.52855 molar glucose solution. Now there's a little bit of important wording here. We're putting this in enough water to make 150 milliliters of solution. We're not putting this in 150 milliliters of water, because molarity is moles of solute per liter of solution. So it's not liter of solvent, it's per liter of solution that we're working with. So be careful when you're looking at problems, when you're building things up. Oftentimes the way things are worded gives you a little hint as to what it's aiming for. One other convention that's going to come up over and over and over again when using molarity is this square bracket convention. So if I put something in square brackets, I'm almost always talking about a solution and units of molarity. So if you see something like glucose in square brackets, what it's really saying there is I have a solution of glucose, and in units of molarity, its concentration is 0.52855 molar. So we're going to see that square bracket convention come up fairly often, which is why I paused a moment to mention it here. Now, glucose is a molecular solute, right? Glucose is a molecule. It stays molecule when it dissolves in solution. What happens if I use something that's not glucose? What if I use something that's ionic and make a solution? Well, that makes a lot of it is the same approach, but we also have some more information that we can get out of these calculations if we really want to. So what's the molarity of solution made by dissolving 26.714 grams of magnesium nitrate in enough water to make 450 milliliters of solution? So that looks just like the glucose problem, and we put it together exactly the same way. So 26.714 grams of magnesium nitrate divided by the formula mass of magnesium nitrate is 148.313. I added that up off the periodic table. Divide by 0.45000 liters gets me a molarity of magnesium nitrate of 0.40026 molar. So same as the last problem. But now, because we're an ionic compound, those magnesium ions and nitrate ions break apart and separate in solution. So we can talk about what is the concentration of magnesium ions. And here I'm using that square bracket convention. So what is the concentration of magnesium ions in units of molarity? Well, I know that the concentration is 0.40026 moles of magnesium nitrate per liter of solution. So now I can use an extra term here. This kind of looks like a stoichiometry term, doesn't it? Well, this is sort of a little micro stoichiometry problem. But for every 1 mole of magnesium nitrate that I dissolve, I get 1 mole of magnesium ions. So multiply by 1 over 1, mathematically not too tough, and we get that this solution is 0.40026 molar magnesium plus 2 ions in solution. What about nitrate? Well, nitrate, again, it's 0.40026 molar magnesium nitrate solution, but now every mole of magnesium nitrate that dissolves gives me 2 moles of nitrate ions. So the concentration of nitrate ions in this solution is 0.80053 molar nitrate ions. So when we're talking about ionic species and ionic solutions, we can have multiple different ways to describe the concentration depending on specifically what we want to talk about, depending specifically what we're interested in. How about finding moles? I said that's one of the big advantages of molarity as a concentration unit. So how many moles of glucose are in 150 milliliters of a 1.083 molar glucose solution? 1.083 moles per liter glucose. I've got 150 milliliters of that glucose, and multiply that out, units cancel, I get 0.1624 moles of glucose. Do you remember what the formula is for glucose? We used it a couple slides ago. Do we need to know what the formula is for glucose? Doesn't look like it anywhere in this calculation, and that's one of the really good things, one of the really positive things about concentration. Once I know the concentration, I'm already in moles. Once I know the molar concentration, I'm already in moles. So I don't have to really know what the chemical identity of something is in order to work with it in a solution. So glucose, whatever glucose happens to be, I know how many moles there are because I know the molar concentration and the volume that I'm being used. Similarly, if we look at how many moles of chloride ions are in 150 milliliters of a 1.083 molar solution of magnesium chloride, well, similarly, magnesium chloride, 1.083 moles per liter, times the amount that we're using, 150 milliliters. But now, again, as an ionic, we need to add that one extra step here. So for every mole of magnesium chloride, I've got 2 moles of chloride ions. So I've got to factor in that 1:2 ratio, and I get 0.3249 moles of chloride ions. So that gets us moles out of molarity. What else are we going to do? Well, oftentimes when we're using a solution, it's convenient for us to make a very concentrated, relative term, concentrated solution that we then use to make more dilute solutions. So how do we calculate, how do we figure out those dilutions? And dilutions have the deceptive advantage of dilutions can be calculated with an almost deceptively easy little equation here. C1V1 equals C2V2. Concentration 1 times volume 1 equals concentration 2 times volume 2. And this works for most concentration units, which is pretty convenient. As long as you're using the same concentration and volume on both sides, you can use this for just about any concentration unit, just about any volume unit, and you should get a good result. So here's a problem. You have diluted 28.39 milliliters of a 0.6482 molar ethylene glycol solution to a total volume of 250 milliliters. What is the new concentration of ethylene glycol? Do we know what ethylene glycol is? You might. You could look it up. But again, once we know its molar concentration, we don't really need to know the identity of ethylene glycol, because this is telling us something about how many moles we're working with. So plugging into C1V1 equals C2V2, we've got what? C1, concentration 1.6482 molar times 28.39 milliliters is equal to C2 times 250 milliliters. And again, we don't have to switch this to liters as long as we've got milliliters on both sides. Calculating that out, C2 is 0.07361 molar ethylene glycol. Make sure your dilutions are going in the right direction, right? This time I'm diluting a pretty small amount to, almost 10 times its volume. So my concentration should be almost 1/10 of this. So that's a little over 1/10. Looks pretty reasonable. Let's use this in a little bit different direction. An unknown volume of 1.725 molar sodium ions And again, here we're just using sodium ions because we don't care what the other ion is. We know there has to be an anion in that solution. But whether it's nitrate or chloride or sulfate or any number of other things doesn't really matter. We're just focused on the sodium in this case. So an unknown volume of that sodium solution is diluted to 750 milliliters, and the new concentration is found to be 0.8293 molar. What was the unknown volume? Well, again, just plug into C1V1 equals C2V2 and solve it out. And we get that original volume was 360 milliliters. And again, quick check, the concentration went down by about half. So the original amount should have been about half of what was of the total volume in condition 2. The most challenging part about this formula ends up being just keeping condition 1 and condition 2 matched up together. So similar to gas laws, as long as you can keep your 1s and your 2s matched up together, it's a pretty simple formula for you to use. We're going to be looking at a lot of different places where molarity is used in a variety of different ways, both in stoichiometry problems and in dilution problems. So make sure you get plenty of practice, and see you next time.